Okay, so we talked about how we can associate a matrix with a linear map. Now we're going to go the other way and say any matrix can represent a linear map. Okay, so really linear maps and matrices are two different ways of representing the same thing. Okay, so the previous subsection shows how to start with a linear map and create a matrix representation. What about the converse? So, as we just said, start with a matrix and create a linear map. So if I fix this matrix H and fix the domain and codomain, suppose I take the standard basis in R2 and I take this basis, 1 minus x, 1 plus x, which is a basis in P1. Is there a linear map between the spaces associated with the matrix? And the answer, of course, is yes, otherwise they wouldn't be asking the question. And consider H from R2 to P1 defined as follows. For any domain vector V, represent it with respect to the domain basis, multiply that representation by the matrix H, and then H of V is the codomain vector represented by the result. We will verify that H is a linear function. Okay, before we go there, I drew this little picture to show kind of what's going on. If we have a linear map from vector space V to vector space W. In order to associate that with a matrix, we take the representation of vectors in V with respect to a fixed basis, and that will take us down to Rn, where n is equal to the dimension of V. So dimension of V is equal to n. Okay. Now, if once we have a representation in Rn, we can multiply that by a matrix. And H is going to be an m by n matrix. So that when we multiply a vector in Rn by a m by n matrix, we get a vector in Rm. And then we can take the inverse of the representation map to take us back to W. Here we have the dimension of W is equal to m. Okay. So we can duplicate the action of H going directly from V to W by first taking the representation, then multiplying by the matrix, then going back to the vector space here. This kind of diagram is called a commutative diagram. It's very commonly seen in algebra. Okay. All right, now let's go back to the task at hand to verify that this function H, defined by this process, is a linear function. First of all, we need to verify that it is a function. In other words, every unique vector V has a unique output H of V. Okay, so given the V, we need to show there's a unique output H of V. And so this uniqueness happens because the representation of a vector with respect to a basis can be done in one and only one way, as in this picture. There's a unique image of for every vector in here, there's a unique image here in Rn. Actually, the proof of uniqueness follows this diagram, because for each vector V in here, there's a unique point in here, which is the representation. Then there's a unique point over here, that's the matrix multiplied by the representation. And then there's a unique point back here in W, which is the representation, which has this point as a representation. Well, he's going to say that in words here. So there's one and only one representation for V. Okay. And let's show now that H is linear. Take any two vectors in the domain and represent them with respect to the domain basis. The representation of U is rep B of U, and the representation of D is rep, this should be rep B, sorry. Let's see. This should be rep B, sorry. So we're going to take this linear combination of representations and multiply by the matrix H. Okay? We're using this particular matrix H, but in fact, in general, it's going to work the same way. We multiply this matrix by the linear combination. By the linearity of matrix multiplication, we can break this up into its two separate factors. You can follow the algebra step by step if you like. Now this here is equal to the representation of H of U in the D basis. This here is the representation of H of V in the D basis. Now by the linearity of the rep D map, I can write this as rep D of C times H of U plus D times H of V. Okay. Now what does that tell us? Here we started out with Cu plus, I'm sorry, that's H of W, shouldn't be V. Actually, this should be a V here. There's a mistake here. We started out with Cu plus dV. Okay. And we went through and we computed H of Cu plus dV, and we arrived at this. Now, when you look back at this picture here, we found the representation down here. When we take the rep inverse, we remove this rep D, and that takes us back to CH of U plus DH of V. Okay. So we started out with Cu plus dV. We take H of that by going through the commutative diagram. So I'm going to evaluate H of Cu plus dV. And I go through these steps. I end up with this result, which is the usual linearity result. Okay. All right. The next result verifies that the above calculation works for all matrices, spaces of suitable dimension, and bases. Theorem: any matrix represents a homomorphism between vector spaces of appropriate dimensions with respect to any pair of bases. Now in this argument, we're just going to generalize what we did before. You're going to show that the linearity property by this commutative diagram method, going first here, then over here, then back up here. Okay, first, we must check that for any matrix H and any domain and codomain bases B and D, the defined map H is linear. All right, that's what we just did in the special case. If V and U are vectors such that the representation of V has these coordinates and the representation of U has these coordinates, then, just as we did before, we take H of CV plus DU. Okay? Now, how do we get this result here? Well, let me first fill in the missing step. Since rep B of V is these coordinates and rep B of U is these coordinates, then we would have rep B of CV1 plus UV plus, plus of CV plus plus DU. Let me write that a little bit more neatly. Okay, rep B of CV plus DU is equal to, well, it's going to be CV1 plus DU1 all the way down to CVN plus DUN. And that's true because we know the representation map is linear. All right? Now, since these are the coordinates of CV plus du, we can find h acting on this vector by applying the matrix to this column vector. Okay. And if you think about how that works, this is the first column of the matrix dotted with the components of CV plus du times the first basis vector in the D basis, plus and so on all the way up to the last column of the matrix times the, I'm sorry, I said first column, should be first row. This is the first row of the matrix times the column vector multiplied by the first basis vector. And then you're going to have the second row of the matrix times the column vector times the second basis vector all the way up to the mth row of the matrix times the column vector times the mth basis vector. So this really expresses the matrix H multiplied by this column vector, and each component of the result is multiplied by the corresponding basis vector in the D basis. And that gives us the proof. So let's now connect some properties of linear maps with properties of the associated matrices. First, we observe that if H is the zero map, and if H is the zero map, then the matrix that represents it must be the zero matrix. Okay, how do we see that? First, assume that H is the zero map. Okay. Then for any basis, we have that H operating on any basis vector is going to give me the zero vector. And this is represented with respect to the co-domain basis as a column vector of zeros. Now remember, to get the matrix that represents the mapping, we take the representation of H of each basis vector in the codomain basis. But since the codomain vectors are always zeros, the entire matrix is going to be a zero matrix. All right. Now here we're trying to show that the mapping is a zero map if and only if it's represented by the zero matrix. We've shown that a zero map is represented by a zero matrix. Now we want to show that a zero matrix represents a zero map. And that you can just do by evaluating the mapping. Suppose there are bases B and D such that rep BD of H is the zero matrix. So we're now going to show that a zero matrix gives a zero map. Then for each beta I in the domain basis, we have that its representation in the codomain basis is a column vector of zeros. Okay, that's the definition of matrix of linear transformation. So H acting on each basis vector must be 0. Now if H acting on each basis vector is 0, and since all vectors are linear combinations of basis vectors, that's going to tell us that H acting on all vectors in the domain are 0. Okay, so zero matrix is the same thing as zero linear transformation, or zero linear map rather. Okay, so here's one example. The zero map from R2 to R3 is represented by a 3×2 matrix of zeros. Now, notice that the codomain dimension is the number of rows, and the domain dimension is the number of columns. And that makes sense because you're going to multiply this matrix by a vector that represents the elements of R2. In order to make this representation work, you need to have as many components here as you have dimension for this domain. On the other hand, the result is going to be a representation of a vector in R3. So you need as many components in each column as you have dimension of the codomain. Okay. So just try to remember, a mapping from R2 to R3 is going to be a 3 by 2 matrix. A mapping from Rn to Rm is going to be a m by n matrix. All right, another theorem. The rank of a matrix equals the rank of any map that it represents. Okay. So when we talk about the rank of a map, what that means is that's the dimension of the range. Right? And the rank of a matrix is equal to the rank of its column space. Okay. So let's see if we can equate those two. The rank of a matrix, so this is the dimension of column space. I'm not sure why it's the dimension of the column space. And here, the rank of the map is equal to the dimension of the range. Okay, so those two things should be equal. All right, for the proof, suppose the matrix H is m by n. All right, remember, we just got finished saying that m is going to be the dimension of the codomain, n is going to be the dimension of the domain. Okay, so we fix domain and codomain spaces V and W of dimension n and m with bases beta 1 through beta n of the domain and D, which is delta 1 through delta m for the codomain. Then H represents some linear map between these spaces with respect to these bases. The range space of this linear map is going to be H of all possible linear combinations of the basis vectors. Now, by linearity of this map H, that's the same thing as taking all possible linear combinations of the maps or images of the basis vectors. Okay, so what does that tell us? That tells us that the range space, which is the space consisting of all possible images of H, is spanned by H of the basis vectors. Now, the rank of the map H is the dimension of this range space by definition. Okay. We want to identify that with the dimension of the column space of the corresponding matrix. Okay, let's see how that's done. Now, the rank of the matrix is the dimension of its column space, which is the span of the set of columns. And remember how you define the matrix. You take the representation with respect to the range, the codomain basis of the images of all of the basis vectors. Now we want to show that these two spans have the same dimension. Okay, so it says from the proof of lemma I25, if we fix a basis, then representation with respect to that basis gives an isomorphism. So that's a way of finding, that's the standard way of finding an isomorphism between a vector space and Rm, where m is the same as the dimension of the vector space. Under this isomorphism, there's a linear relationship among members of the range space if and only if the same relationship holds in the column space. We've seen when we have two isomorphic vector spaces that linear relationships here have one-to-one and onto correspondence with linear relations here. Okay, so we have a linear relationship here with the W's if and only if we have a linear relationship with the corresponding vectors here, which are the representations. Okay, so that's expressing this, that if we have a linear relationship between vectors in W, then it must be true that the same linear relationship holds between representations of those vectors. It follows that a subset of the range space is linearly independent if and only if the corresponding subset of the column space is also linearly independent. Okay, so like we said here, these are the vectors that span the range space. These are the vectors that span the column space, and you can associate linear relations with one with linear relations with the other. So it's the size of the largest linearly independent subset of the range space is equal to the size of the largest linearly independent subset of the column space, which means the two spaces must have the same dimension. All right, let's do an example. It's always good to make things specific with an example. Consider this mapping from R2 to R2 that takes this 2 by 1 vector to this 2 by 1 vector. Now you can see something here. These two are the same. These two components are always the same, so the map lies on the line x equals y. This is a one-dimensional vector space, so the rank of the map is 1 because that's the dimension of the range. We can look at two different matrices that represent this map. We've seen before that there are multiple matrices that represent the same map depending on your choice of range and domain, of codomain and domain basis. So let's look first in the case where the matrix is found using the standard bases, and in the second case we'll use this different basis that we used. Now in the standard basis, the calculation is easy, so the other basis is more representative. We try that. Okay. Now since we're looking at the mapping from the domain to the codomain, this calculation comes about here because we need to find the representation with respect to the D basis of the images of these basis vectors. So we need to find rep D of H of 1, 1. Now what's H of 1, 1? Well, if we take in 1, 1, it's going to go to 2 minus 1, which is 1, 2 minus 1, which is 1. So that's what this 1, 1 here is. You shouldn't confuse this. This 1, 1 just happens to be the same as the first basis vector, but that's just coincidence. Really what we're looking for is the representation with respect to the D basis of the image of 1, 1. Right. And you can work out that if you represent this vector in terms of this basis, you're getting 2, 3. Okay, again, you can verify that anyway, that 2 times 1/2 plus 3 times 1/3 gives me 1, 1. On the other hand, the image of H of minus 1, 1, what do we get for that? You're going to get 2 times minus 1, that's minus 3. It's going to be minus 3, 3. So we need the representation with respect to the D basis of minus 3, 3. And you can again verify that to represent this vector in terms of this basis, you need minus 6, minus 9. Okay? So the representation of T with respect to the BD basis is equal to 2, 3 first column minus 6, minus 9 second column. And the representation with respect to the standard basis, you should be able to work this out, is 2, 2 minus 1, minus 1. Okay. All right, and then you can see that the dimension of the column space here is 1, which is the same as the rank of the map. All right. Dimension of the column space here is 1, and that's the same as the rank of the map. Okay? So these matrices are different depending on the bases, but the ranks are always the same. Corollary. Let H be a linear map represented by a matrix H. Then H is onto if and only if the rank of the matrix H is equal to the number of its rows, and H is 1 to 1 if and only if the rank of H is equal to the number of its columns. All right. So here we're going to need to relate the size of the matrix to the dimensions of the domain and codomain. And as I mentioned already, the number of columns is equal to the dimension of the domain, and the number of rows is equal to the dimension of the codomain. Now, if the rank is equal to the dimension of the codomain, that means that the linear map is onto. If the rank is equal to the dimension of the domain, that means it's one-to-one. Okay. So for the onto half, and this is the proof, the dimension of the range space of H is equal to the rank of H, which is equal to the rank of the matrix H by the theorem. Since the dimension of the codomain is the number of rows, if the rank of H is equal to the number of rows, then the dimension of the range space is equal to the dimension of the codomain. But a subspace with the same dimension as its superspace must equal the superspace. Okay, because you can't have n-dimensional space as a proper subset of an n-dimensional space. So that gives me the onto part of this result. All right, for the other half, a linear map is one-to-one if and only if it is an isomorphism between its domain and its range. That is, if and only if its domain has the same dimension as its range. The number of columns in H is the dimension of the domain. And by the theorem, the rank of H is equal to the dimension of H's range. Okay. Another example. Let's take the rotation matrix. It turns out that this matrix has this form for rotation by angle theta. We talked about this before. You can find this by taking the rotation of the two standard basis vectors, and you use trigonometry to show that the rotated vector 1, 0 becomes cos theta minus sine theta. And the rotated, oh, I'm sorry, is he doing counterclockwise? There's actually a mistake here. This should be a plus sine theta here, and this should be a minus sine theta here. Because the rotated 1, 0 basis vector is going to be cos theta sine theta. You can see that from trigonometry. And the rotated 0, 1 vector is going to be minus sine theta cos theta. Okay. So when you do the pi over 4, the matrix is going to be like this. And notice that this matrix has rank 2. Okay. Now we go on to singular and non-singular maps. This has to do with the rank. A linear map that is one-to-one and onto is non-singular. Otherwise, it's singular. A linear map is non-singular if and only if it's an isomorphism. Remember, a map is a homomorphism is isomorphism that's not necessarily one-to-one and onto. The only difference between a linear map and an isomorphism is that isomorphism is also one-to-one and onto. All right. To prove this, we first prove a lemma. A non-singular linear map is represented by a square matrix. A square matrix represents non-singular maps if and only if it's a non-singular matrix. Thus, a matrix represents an isomorphism if and only if it's square and non-singular. Okay, the proof. Assume that H is a non-singular map. The corollary that we just showed, that any matrix representing that map, since H is onto, the number of rows of H should equal the rank of H. And because H is one-to-one, the number of columns of H should also equal the rank of H. Therefore, H must be square. Okay, one-to-one gives me one equality, and onto gives me the other equality. And that gives everything is equal all around. Next, let's assume that H is square. The matrix H is non-singular if and only if its row rank is n, which is true if and only if H's rank is n by Theorem 2. So the row rank is equal to the rank. which is true if and only if H's rank is n, which is true if and only if H is an isomorphism. And this last holds because the domain of H is n-dimensional as it's the number of columns in the matrix H. Okay, an example. This matrix is non-singular. By inspection, its two rows form linearly independent sets, so we can see that it's non-singular. So any map with any domain and any codomain with any possible pair of bases that's represented by this matrix will be an isomorphism. Okay. All right. Now Gauss's method can show that this map is singular. Okay, you'll show that these three rows are not linearly independent. So any map that it represents will be a homomorphism that's not an isomorphism. And that's the end.